All right, can everyone hear me? Yes, great. Okay, first I'll thank the organizers for inviting me to give this talk. I'm going to be talking about waveform modeling using gravitational self-force. So what are gravitational self-force waveform models? They are the primary models that will be used for MREs for LISA. So if we refer back to the kind of picture we saw in Martin's talk yesterday, no, 2 days ago, in different regions of the binary parameter space, we want to use different models. So if the orbital separation was on the y-axis here and the large mass ratio on the x-axis, we are looking down here where you have one object much larger than the other. So it's the MRE regime. But as I'll mention later, this model actually goes pretty far towards the comparable mass regime as well. So that's the big picture. What are the models for? But what can we say about them otherwise? So remember, Martin described kind of first principles models that directly solve the Einstein equations, and then effective models or models that combine information. Self-force models are first principles models. They're directly solving the Einstein equations. But they're also fast. So these are models we get from first principles, but we ultimately are able to generate waveforms very, very rapidly in a time scale of 10 milliseconds or so. The best models we've got are also quite accurate. So if Q here is the large mass ratio, the most accurate model we currently have has an error in the phase of about 7 divided by the mass ratio. So for an MRE where Q is 1,000,000 or 100,000, this is a tiny, tiny, tiny fraction of a radian. And this is over the last 10 Schwarzschild radii. But even for an IMRI with a mass ratio of 1 to 100, it's a very small error in the phase. So this is great. We got a fast model. We got a first principles model. We got an accurate model. What we don't have is a complete model. So the real big challenge right now in self-force modeling is just covering the parameter space. So our best model, the one I mentioned here, that I'll get to later, is very restricted in parameter space. It's quasi-circular. It's slowly spinning. We know that for MREs, we are very likely to need high eccentricity. We definitely need rapid spin. We need spin precession. We need everything. So this is the big barrier right now. Okay, but how do we build these models? I'll skip almost all the technical details, but the basic idea is we've got a large black hole. We've got a small body orbiting around it. In general, they're both spinning. Let me introduce the small mass ratio, so 1 over the large mass ratio, which is much, much less than 1. And self-force theory is fundamentally a perturbative method. It's an asymptotic approximation where we are saying the space-time metric is approximately the Kerr metric of the large Kerr black hole plus small corrections coming from the small body. So I'm very deliberately going up to second order in my small parameter here. Then these small perturbations to the space-time geometry react back on the small body and accelerate it away from geodesic motion. So if it were a perfect test particle, its acceleration would be 0. But because of these perturbations, you have small accelerations. And we call these the self-force. Most of the model development relies on kind of the structure of the 0th order approximation. So at 0th order, we do have just a test particle. So it's a test mass orbiting around a Kerr black hole. It's moving on a geodesic of the Kerr black hole. These orbits are very complicated looking. But you can describe them quite simply if you choose your coordinates wisely. So these are integrable orbits, meaning they have 3 constants of motion: the energy, the angular momentum around the spin axis of the large black hole, and something called the Carter constant, which is related to the inclination of the orbit. Then in addition, we have 2 more parameters. We have the mass of the large black hole and its spin. So we have this set of constants, and then we have 3 phases of motion. So this motion is tri-periodic. It has 3 frequencies corresponding to 3 different types of motion, round and around, in and out, and up and down. And you can choose these phases to have constant frequencies. So then this complicated motion we can describe very simply with a few simple ODEs. We have constants, which have 0 rate of change. We have frequencies constructed from those constants. And then we have phases that grow exactly linearly in time. So this is the 0th order problem. Once we go into perturbation theory and are accounting for the corrections to the metric and the corrections to the motion, those governing evolution equations don't change all that much. You can still choose coordinates very wisely. So I'm putting little tildes on here because these are not the same coordinates, but they're as close as we can make them. We can still say we've got phases that have frequencies that are almost constant, but not quite. They have a slow rate of change. So all of your parameters of your system are slowly evolving. The mass and spin of the primary, the energy, the angular momentum, and the Carter constant are all slowly changing. So the rate of change is of order epsilon. So what we do is we devise a method of solving the Einstein equations using this construction of the orbital motion. And then at the end of the day, what comes out is a waveform with a very nice, simple structure where we've got these mode amplitudes that have a bunch of mode numbers, but the key thing is they're only functions of the slowly varying parameters of the system. So these amplitudes are slowly changing with time. And then we have phase factors that encode the phases of motion of the orbit. So you have slow amplitudes and rapid phase factors. I haven't mentioned secondary spin, but that fits neatly into this picture as well. If you add a spin on the secondary object, all it changes is you pick up some new slowly evolving parameters, and at sufficiently high order, you pick up a new precession phase corresponding to the precession of the secondary spin. Now, this method is very nice for 2 reasons. One is it's a practical method of solving the Einstein equations. It's actually the only method we know how to do at second order in perturbation theory. But also, it enables the rapid waveform generation that I mentioned. So the way it does that is it allows a nice clean split between offline steps, pre-computing data, and then very rapid online waveform generation. So in the offline step, you solve the Einstein equations, you compute all these mode amplitudes, you compute the forcing functions that appeared in those simple ODEs I showed you. You compute all of these on a grid of parameter values. So then you have all the necessary input for the waveform. Because to generate the waveform, all you need is these forcing functions. You then solve those very simple ODEs. You get the trajectory through phase space, or through the parameter space. And then the waveform was just a very simple function of that trajectory. So as soon as you get the trajectory, you immediately have the waveform. And over the past few years, a software package has been developed called FEW, Fast Emery Waveforms, that can do these steps incredibly rapidly. Even when we have tens of thousands of mode amplitudes, we can still generate waveforms on the order of 10 milliseconds. So I think it was yesterday, Lorenzo Sperry gave a talk on this software package. And there's also a poster by Christian Chapman-Bird. So we have a method that we say is accurate. We say it's fast. How accurate do we actually need it to be? And by that I mean, how high order in our perturbative expansion do we need to go? So the estimate for how high order we need to go is based on the long-term behavior of these orbital phases, because they directly encode the phases of the waveform. And on long time scales, the orbital phases have an expansion that looks like this. They start at 1 over the small parameter. The smaller the mass ratio, the longer the inspiral lasts, the more phase you accumulate. Then you have a correction that's epsilon to the 0, so almost mass ratio independent. And then you have higher order terms. And so just based on this construction, we can estimate, okay, for sufficiently small epsilon, if we include these first 2 terms, we have a phase error that's going to be sufficiently small. So for an Emery, we expect this term and the higher order terms to be 10 to the minus 5 radians, roughly. But even for an Emery, mass ratio 1 to 100, it's of order 1 over 100. So over the past 15 or 20 years, the goal has been basically to compute the needed inputs for these two terms. And more recently, we have parameter estimation studies that actually really back this up with estimates of the parameter bias you will incur if you, for example, ignore this term. And we see that we really do need both of these terms, but with just these two terms, you get incredible precision in your parameter estimation, and you don't need the higher order terms. Okay, so what do we need for these first two terms? This first term we call adiabatic order, or 0 PA. This is entirely determined by the leading order forcing function in those ODEs that I showed you. And that leading order forcing function is constructed from the dissipative piece of the first order self-force. So that means we need to solve the first order Einstein equation, or at least part of it, to get this forcing function and to get the waveform out. The next term is called first post-adiabatic, or 1 PA. For that, you need the subleading forcing function in those ODEs I showed you. And to get that forcing function, you need a dissipative piece of the second order self-force, which means you need to solve at least part of the second order Einstein equation, so second order in the mass ratio. You also need the full conservative self-force, first order, and secondary spin effects enter exactly at this order, but you only need them to linear order in the spin. So based on this, we know we need to solve the first order Einstein equations completely, and at least part of the second order Einstein equations to get this second order self-force. Now here I skipped a bit. For MREs, when you have these three frequencies, you can get orbital resonances between the frequencies. And if you encounter an orbital resonance, a term actually appears in between these two orders, so what we call 0.5 PA, which is also, of course, very important. And I'll come back to that a bit later in the talk. Okay, so big picture, the goal for quite a long time in the self-force community and in the MRE modeling community has been to get 1 PA accuracy over the full parameter space. So I don't expect you to absorb all of this table. You can look this table up in the working group, the Waveform working group white paper that came out last November. The basic idea is we want to fill all of these boxes with 3 check marks. When we do that, we will have generic, inclined, eccentric, precessing orbits and waveforms around a Kerr black hole. We will have orbital resonances. We will have secondary spin. We'll have everything. So we have covered a lot of this parameter space, but you see a whole lot of X's in some places, so we still have a lot of work to do. So over the rest of the talk, I'll kind of go through step by step, showing you what we currently have, what is the current state of the art in parameter space coverage and in accuracy. Okay, in terms of covering the parameter space, at 0 PA order, we are doing pretty well. We have mostly covered the parameter space for generic orbits and Kerr. So when I say generic orbits and Kerr, again, this is what I mean. These are inclined, eccentric orbits that are evolving inward and eventually plunging into the spinning black hole. So implemented in the Few software package, we do have generic orbits in Kerr, but in a weak field, small eccentricity expansion. So in post-Newtonian counting, we have 5.5 PN, and in powers of eccentricity, up to e to the 10. So this covers a big chunk of parameter space, but not everything. Then for fully relativistic waveforms, implemented in Few and should be coming out in a paper imminently, we have fully relativistic waveforms for equatorial orbits in Kerr, so no inclination. And the kind of waveforms you get out from the fully generic ones, from these ones here, look like this, so very complicated waveforms. Okay, so that's where we're covering the most parameter space. That's at 0 PA order. Lots of people have been making progress towards including all the necessary 1 PA effects. So for example, secondary spin, a lot of work being done in the Prague groups, and Lisa Drummond and Scott Hughes at MIT. And so we do have some waveforms to look even more complicated. So I'll say they're roughly available. They're not actually available in Few, but again, that should happen fairly soon, hopefully. So we have 1 PA waveforms that include the conservative spin effects. We also need dissipative spin effects associated with rates of change of things. That's also in the pipeline. There's a little bit of work that needs to be done to fill that last bit in. So there was a talk on these kinds of waveforms by Lisa Drummond yesterday, and there's a poster by Wojciech Brycani. Okay, as I mentioned, in between 0 PA and 1 PA, we have 0.5 PA. These are orbital resonances. So what happens at an orbital resonance? Okay, here I'm plotting the three frequencies, the three fundamental frequencies of orbital motion in Kerr. And when the radial frequency divided by the polar frequency becomes rational, you have a resonance. And so during a resonance, things that were otherwise oscillatory, they become stationary, and then they accumulate more than they would have outside the resonance. Now, if you look at just these plots of the frequencies, you don't see anything in particular happening. But if you zoom in on the resonance, basically you get a little tiny jump. So this is the change in the frequencies across the resonance. This is a mock-up model. This is not a real value of the frequency jump. That should be implemented soon based on the 5.5 PN model I mentioned. But this shows you the qualitative behavior. So you get a little tiny jump in the frequency across the resonance, but that little change in the frequency leads to a long-term change in the phase. So here we are plotting the change in each of the three phases of motion. So this is what I was calling curly phi tilde on previous slides. And so up to resonance, you have no change. This is now the change you get by including the resonance. So it's on the order of a few radians, and that is what we expect for the realistic case as well. And so Phil Lynch talked about this yesterday, and I got these images from Christian. The images from Christian come from work with Niels Warburton on actually including these resonances into Phi. And again, this is the waveform around the resonance, and in this vicinity is being plotted the 0 PA waveform and the waveform that includes the resonance, and you see no difference. But if you look at a much later time, all of a sudden you're seeing huge dephasing if you don't include the resonance. So this should be implemented in Phi imminently. Okay, all of that is about covering all the qualitative ingredients, covering the parameter space. But as I mentioned, the goal is to get 1 PA accuracy over the whole parameter space. So where are we with 1 PA waveforms? Here I'm showing you the best model we currently have. So this is the outcome of very long collaboration between Southampton, myself, and people at UCD. And now we have a much larger group of collaborators all working on developing these 1 PA waveforms. Here I'm comparing against the numeric relativity waveform in black. This is for a mass ratio of 8, so not an emery at all, but there don't exist, and there will very likely never exist in our lifetimes, emery waveforms from NR. So this is the thing we can compare against. It's much more in the comparable mass regime. So mass ratio 1 to 8. As I said, in black, this is the numerical relativity waveform, which we can treat as roughly exact. And in green is our 1 PA waveform. So this is a case with a small spin on the primary. We can't handle full generic spin on the primary yet. And this is with a very rapid spin on the secondary. These are anti-aligned, but we also have a model where the secondary spin is not aligned with anything. And here we see that even for mass ratio 1 to 8, we accumulate almost no phase error until quite late in the in-spiral. So this here is just zooming in on this little patch at the end. But then we rapidly dephase towards the end. So this is the best model we've currently got. Quasi-circular, slowly spinning primary, generic secondary spin. This has been implemented in Phi, except not yet the primary slow spin, but we can add that anytime. I don't know why we haven't added that. And we don't have yet the precessing secondary spin added to the Phi model, but again, that can be added easily. Okay, so this is the best current model. One thing you'll notice about it is that it just stops. It's not that it rapidly dephases. I mean, it does rapidly dephase, but then it also just stops. So that's because this whole expansion method I described, this has nothing to do with the small mass ratio, this has nothing to do with the self-force formalism, this is all to do with that multi-scale framework I mentioned, where the underlying assumption is that you have slow evolution of the parameters of the system. And that is what breaks down right at the end. Now for MREs with mass ratio of 1 million or something, we really don't care about this last little bit because it contributes so little to the SNR. But for IMREs, or for mass ratios 1 to 50, then we do care about including these last few cycles, including the merger. And so here's a model we are developing with Jeffrey Compere and my postdoc Lorenzo Kukler. This is a model that includes the final merger. This is still doing first principles self-force calculations, but using different methods in each regime. So here is the 1 PA multi-scale, 2-time scale framework I showed you before. Then as the small object gets close to the innermost stable circular orbit, it transitions into a different dynamics, which we call the transition to plunge. We use a different model there. We're going to next to leading order in that approximation. And then you have a very rapid plunge of the small companion into the big black hole. That generates the merger signal and the ring down at the end. So we have all of this, and we can implement this in Few. That's underway. And so we will ultimately have full in-spiral merger ring down waveform signals on the time scale of a few tens of milliseconds. That is in the pipeline, but again, limited to quasi-circular, slowly spinning binaries. And Lorenzo Kukler will talk more about this model tomorrow. Okay, so just to wrap up, what is the state of self-force waveform modeling? So originally, self-force waveforms were really just designed for MREs. We now recognize that they are very accurate for IMREs, and even for mass ratios down to 1 to 20, 1 to 30, or even 1 to 10. But we only know that about quasi-circular binaries. But we do expect these to be accurate over the whole range of IMREs for generic orbits and MREs. This method, as I kept emphasizing, gives us a native fast waveform generation framework, which is definitely fast enough for current data analysis studies. People tell us it might not be fast enough for the global fit. We'll have to see. It might need additional acceleration. As I mentioned, at 0 PA order, so leading order accuracy, we have equatorial in-spirals into a Kerr primary. We have generic in-spirals, but in a weak field approximation. Ongoing work is including resonances, secondary spin, and fully relativistic inclination precession. And the ultimate goal is to get complete 1 PA waveforms over the full parameter space. What we currently have is quasi-circular in-spirals into slowly spinning primaries with generic spin on the secondary. So the big picture here is we know how to do most things, but there are major obstacles in covering the full parameter space on the time scale of LISA. So I think yesterday there was a mention of 10 years being a very short time scale in astronomy, 10 years, a very long time scale in astronomy. In waveform modeling, that's a very, very short time. It took us almost 30 years to get these 1 PA waveforms I showed you. So it's actually a race against time to get the full thing by LISA. Suichiro yesterday gave a talk about covering the parameter space more efficiently, possibly, at least for present-day data analysis studies. What I didn't mention, just for lack of time, was going beyond the vacuum GR case. There's a lot of work going on to include environmental effects and deviations from GR. So I'll refer you to Andrea's talk later today and to Andrew Spire's talk yesterday. Okay, thank you.
Okay, thank you very much. Questions? See at the back here.
Thanks. That was a very nice talk, and the news about the IMRI waveforms is extremely comforting. My question is about eccentricity. So we've heard before that there's no unique definition for that, and of course, in the LISA band there might be substantial eccentricity. And so I'm wondering if you could talk a little bit about what the limitations are and what the path is forwards on that.
So we know how to do eccentricity at 0 PA. That has been done. There's a very good understanding of how to do that. In principle, there's no obstacle to extending our quasi-circular model to include eccentricity. In practice, it's just technically challenging. You have a lot more mode amplitudes you need to calculate. You have a problem that almost all of our calculations are done in the frequency domain. And once you go into frequency domain, an eccentric orbit kind of gets smeared out over radii. And so it's just technical challenges, no fundamental obstacles. In terms of defining eccentricity, in this limit, it's very easy to define everything from the fundamental frequencies, which are almost directly observable in the waveform. So in terms of defining eccentricity, the challenge is much more in comparing between self-force and numerical relativity, for example, rather than a limitation within the self-force.
Thanks.
More questions? Yes.
Thank you so much for the wonderful overview. So maybe a related question. So is it easy or feasible to apply the self-force calculations to unbound orbits?
There's lots of work going on that right now. So Leo Barak has done the most work on that with his students, Ollie Long and Chris Whittle. Right now, that's only been done for a scalar charge. There was a talk about that yesterday by Davide. I'm told that in gravity, that should be done soonish at first order. Pushing it towards second order, we really have not thought about the challenges at all. So it's a different set of challenges. Some things are much easier, some things are much harder.
Thanks.
We have time for a few more questions, if anyone has one. All the way at the side there.
Hi, you talked about the 0.5 PA order resonance effects. Are there similar effects at like 1.5 PA, and would they be important for modeling?
There will be the same effects at 1.5 PA. Whether or not they're important, it's unlikely. So the overall magnitude of the phase correction you get from resonances appears to be significantly smaller than you would expect from just a naive power counting. That's basically because it's, first off, self-force effects are generically, numerically kind of small. So you always get a little bit of suppression relative to the power counting. But also, the jump that you get from the resonance is coming from kind of higher modes, so it's already subleading. And so it's extremely unlikely that we would actually need the 1.5 PA terms. But we can always check. Once we've worked out how to do 1 PA, adding the 1.5 is extremely difficult. Disregard that.
Okay, if there aren't any more questions, we'll thank our speaker again.